into the PowerPoint. Okay, so tonight we're going to continue our discussion on chapter 16, right? So last Wednesday's session, we introduced this chapter. We spent a lot of the time going over buffer and titration challenge problems, but then we introduced KF, which is basically our equilibrium constant for the formation of a solid or the formation of a complex ion. And then we also learned about KSP, our solubility product constant. This is basically the equilibrium constant for the dissociation of a solid, right? So for KSP, you're going to have a solid as a reactant splitting into its ions, right? Because last semester and earlier this semester, we kind of said like dissolves like, right? Polar solvents dissolve polar and ionic solutes, and non-polar solvents dissolve non-polar solutes. But here we're kind of recognizing that was an oversimplification, and that pretty much every solvent will partially dissolve pretty much any solute, right? So we're kind of looking at this case, or in this chapter, we're looking at things that are a little bit soluble in water, but not much. Okay, and so that's where KSP comes in. So tonight we're going to really attack the meat of chapter 16, really kind of coming after these key concepts and really the concepts that you're more likely to see on your exam on Friday, since it's a long answer exam. And so our goal will be to finish the chapter tonight. If we have to push one topic or two topics to Wednesday, we can do that. However, I do think we'll get through everything tonight. And then on Wednesday, I'll be doing a chapter 15 and 16 content review, and we'll have some challenge problems to help you prepare for your long answer exam. So I've actually already started the concepts for the challenge problems. I believe I'll be giving 4. However, all of them will be very, very intensive and have many, many parts, really just so that you get practice doing really anything that they could ask you on the exam. Okay, but luckily I do think this long answer exam will be a little bit more straightforward compared to previous exams. Okay, so I'm going to go through the 4 challenge problems given last Wednesday. If you have any questions about what I just said or any of these challenge problems, again, feel free to unmute yourself or throw it in the chat, and I'll get to it basically as soon as I can. Okay, so here we're told that we have a solution that's made out of silver hydroxide, and the pH of the solution is 9.35 at equilibrium, right? So in a way, this question isn't written the best, but what I really wanted you guys to note is that the pH, this 9.35 pH, is directly due to the dissociation of silver hydroxide. Okay, and so you'll see that on the next slide. And it says, what is the concentration of silver in this solution if the KSP is 9.2 times 10 to the negative 26th? And I actually believe the answer to all 4 multiple choice problems given last Wednesday were B. Okay, so the answer to this one, along with the others, should all be B. And that's just, I don't know, I always put it from lowest to highest, and that's just how it worked out. Okay, but here, right, what we're gonna do is take the pH, and we actually don't care what the pH is. What's more helpful for us is what the pOH is, right? So remember that pH plus pOH always equals 14. And so knowing what the pH is, we can find the pOH, which is 4.65, right? And this represents, or this is equal to, the negative log of our hydroxide concentration. And so we can solve for our hydroxide concentration by doing 10 raised to the negative pOH. So 10 raised to the negative 4.65. And so this is telling us that at equilibrium, or, kind of once this silver hydroxide solid has dissolved as much as it will, right? My hydroxide concentration is going to be 2.24 times 10 to the negative 5th. Okay, and so once we have that value, all I really wanted us to do is plug that into our KSP expression. So our KSP, and this is our overall written equation here, would be equal to the concentration of silver 2 plus times our concentration of hydroxide squared, right? We're going to square our concentration of hydroxide because it has a coefficient of 2. And just realize that we don't need to divide this by silver hydroxide concentration, right? Because our reactant is a solid, and we never include solids in our equilibrium expressions. So KSP will just be our concentration of silver times our concentration of hydroxide squared. Okay, and so my KSP was actually given in the problem, and above from our POH, we found that our hydroxide concentration is 2.24 times 10 to the negative fifth. So I plug that in, and again, remember to square it because again, the coefficient of hydroxide is 2. And so when we solve for the silver concentration needed to be at equilibrium, you find it would have to be 1.83 times 10 to the negative 16th. Okay. And so the fact that the hydroxide concentration and silver concentration are pretty different here probably tells us that there was an initial amount of hydroxide that we weren't initially privy to. But again, we really just wanted to use the POH from equilibrium to find hydroxide concentration and plug that in to solve for what concentration of silver is required to be at KSP, our saturation point. Okay, and so number 2, a saturated solution of strontium carbonate is prepared by dissolving 2.15 times 10 to the negative fifth grams of that solid in 300 milliliters of water at 25 degrees Celsius. So you're asked, what is the KSP for this solid? Okay, so some things, and we'll go over this tonight more in depth as well. Some things to note is I say a saturated solution. So if you have a saturated solution, that by definition means that you are at your KSP. Okay, so the fact that it says a saturated solution says that we're at KSP, and it says 2.15 times 10 to the negative fifth grams are dissolved. That basically means that that amount of grams of strontium carbonate dissolved and ionized into its respective cation and anion. Okay, so we're going to want to use this mass and the volume to solve for the concentration of both of our ions, and then use that to solve for our KSP. Okay, and so the answer to this one again was B. Okay, and so at the top I solved for the molar mass and then kind of realized after that I had actually given that to you, right? But the molar mass of our solid is 147.63 grams. Okay, and so if we start with 2.15 times 10 to the negative fifth grams, I'm going to use my molar mass to convert to moles of strontium carbonate, and then I'm basically going to divide it by our volume in terms of liters to find my molarity of strontium carbonate. Okay, so I find that my molarity is 4.85 times 10 to the negative 7th molar. Okay, and strontium carbonate in relation to each one of its ions is in a 1-to-1 ratio. Okay, so if it's a 4.85 times 10 to the negative 7th molar strontium carbonate, that means that our solution is that value, 4.85 times 10 to the negative 7th molar strontium 2 plus, and that same molarity in terms of carbonate. Okay, and this is at equilibrium because again, it says this is how much dissolved to create this saturated solution. Okay, so now that I know my molarities at equilibrium of both of my ions, right, I'm just going to write my chemical equation so I know what my KSP will be. Okay, so strontium carbonate solid will dissociate into strontium 2 plus and carbonate, right? And so my KSP expression would be equal to my equilibrium concentration of that strontium times the equilibrium concentration of that carbonate, right? And they're both raised to the first power because they both have a coefficient of 1 in my balanced chemical equation. And so what I'm basically doing here is I'm just going to be taking 4.85 times 10 to the negative 7th and squaring it, right? Because I'm basically just doing the concentration of strontium times the concentration of carbonate. They're the same, so I multiply them together by squaring it. And I find that the KSP for this would be 2.35 times 10 to the negative 13th. Okay, any questions on these first two problems? Okay, and just to give you guys a chance to ask questions if there are, I just want to preface these next two questions. These next two questions had to do with the common ion effect. Okay, so if you didn't quite know how to do it because we hadn't covered it yet in SI, that's a topic I had to delay. That's completely fine. Just, kind of keep it in mind for when we go over that topic, because that's the first thing we'll cover tonight after going through these last two problems. Okay, question 3 asks, what is the molar solubility of lead iodide in the presence of 0.085 molar potassium iodide? Now, if you're kind of confused about what molar solubility is, this is actually kind of like a term or jargon that has been used on chemistry exams in the past. Okay, and so don't let it confuse you. Molar solubility just means what is the solubility of your solid, which means in your ICE table, you're basically solving for S or X, right? You're kind of solving for that change. Remember that just to stay consistent, instead of X in our ICE tables, I'm going to use S as our variable, okay? But they're really interchangeable with, again, S kind of standing for our molar solubility. And the KSP of lead iodide was given. Okay, and so again, along with the other multiple choice questions, the answer to this one, I believe, was B. Okay, so this is a common ion effect problem because we are looking at the solubility of lead iodide in a solution that already has one of the ions, right? It has iodine already in it from potassium iodide. Okay, so we're first going to look at our initial amount of iodide. Okay, so if we have 0.085 molar potassium iodide, right, it's a 1-to-1 ratio between iodide and potassium iodide. And so all that's telling us is that we have an initial amount of iodide of 0.085 molar. Okay, and so I'm going to write my ICE table, right? So I'm going to start with my solid as my reactant. So lead iodide solid goes to lead 2 plus 2 I minus, right? 2 iodines. Okay, and I'm gonna write again an ICE table. So for my initial amount, I really don't care what my initial amount of solid was. That's not really going to affect how I solve this problem. Okay, so I put a question mark because there was some initial amount, but again, there is no effect. Okay, we're gonna assume that there's no initial amount of lead because we weren't told anything otherwise. But because of potassium iodide, we are going to have an initial amount of iodine of 0.085 molar. Okay, now for my change section, again, I'm going to put my change in terms of S, which is just what we're going to use in this chapter instead of instead of X. I'm going to keep flipping those in my head by mistake, right? And so for our solid, we really do have a change equal to negative S, right? Because our reactant is going to be converted into product. Okay, but because it's a solid, we kind of ignore it, but the change for our reactant really is minus S in a way. Okay, and so for our product, right, we're gonna have plus S for lead because it has a coefficient of 1, and for iodine, because it has a coefficient of 2, right, we're gonna have plus 2S. And so at equilibrium, our concentration of lead is S, and for iodide or iodine, it's 0.085 plus 2S. Okay, so let's write our KSP expression, right? So our KSP, which is equal to 7.9 times 10 to the negative 9th, is equal to our concentration of lead times our concentration of iodine squared, right? Because again, its coefficient is 2. Okay, and so I'm just going to plug in the next step my equilibrium amounts of both of these ions. So S for lead and 0.085 plus 2S for iodine. And again, it's going to be squared. Okay, now in almost every problem in this chapter, right, the vast majority, I'd say about 99%, of the problems, you can ignore this plus 2s portion whenever you have an initial amount of one of your ions. Okay, so we're going to ignore s just like we did in chapters 14 and 15, right? And that's going to simplify our expression to our KSP 7.9 times 10 to the negative 9th is equal to s, which is our molar solubility, times 0.085 squared. Okay, and we solve for the molar solubility, it comes out to 1.09 times 10 to the negative 6th. Okay, so that is the answer that they're looking for. And if you did do a little check compared to 0.085, you'd realize that S is super small compared to it, much less than 5%. Therefore, by ignoring 2s here, you're not actually changing the answer that you get at the end. Okay. So any questions on this? This is a common ion type question. Really common ion effect. And the thing that makes it this way is that we just have an initial amount of one of our ions, right? We have iodide that's already present due to potassium iodide. Okay. So if there are no questions, question 4 is actually a very, very similar question. So again, this is a common ion effect where we are going to be adding magnesium nitrate to a solution that contains potassium fluoride. And sorry, it's not quite a common ion effect. It's actually more of a creating a precipitate question, so I apologize. Right, so we're going to basically be adding, and this is very similar to what we did back in chapter 4, right? We added 2 salts, right? We have magnesium nitrate, which is a salt. We added it to a solution of potassium fluoride, which again was a salt. And some of these ions, which in this case it's going to be magnesium and fluoride, can combine to produce a precipitate, right? So creating magnesium fluoride. And so we're given the KSP of magnesium fluoride. I could have given you the KF of magnesium fluoride, so kind of the formation of it. Either way, it would have given you the same answer. Okay, and so the answer again here would have been B. We're looking for what concentration of magnesium would be needed to start precipitating magnesium fluoride. Okay, so whenever they ask for the minimum concentration like this, you're really just solving for what concentration of magnesium gets me to my KSP value. Okay, so again, precipitation will start, it doesn't really start at the KSP, but it starts immediately after, right? So even 0.000001 molar after, you know, or so and such, you know, it'll start precipitating. Okay, so from our, sorry, my little thing's blocking it, so I forget what it's added as, but I think it's potassium fluoride. Again, I can't quite see it. From that, we can find that our initial concentration of fluorine is 0.042 molar. Okay, so that's the important value that we need. Now that we know how much fluorine we actually have in this solution already, we're going to write our KSP equation, because again, they gave us the value of the KSP in order to solve for our concentration of magnesium needed. Okay, so magnesium fluoride solid could dissolve into magnesium 2 plus aqueous plus 2F minus aqueous. Now again, this question put it in terms of using ions to form solid. So if you wanted to flip this equation where magnesium reacts with fluorine on the reactant side to form magnesium fluoride, you could have done that. Okay, you just would have needed to solve for your KF, right? Your equilibrium constant in terms of formation, which would just be equal to 1 divided by your KSP. Okay, again, that would be a different, valid method to solve for this problem. Okay, but again, in this case, I put it in terms of my KSP expression. Okay, so I'm going to make an ice table, right? So my initial amount of fluorine, because it's already dissolved in the solution, is 0.042 molar, right? And my change for magnesium is going to be plus S, and fluorine is going to be plus 2S, again, because its coefficient is 2. Okay, so once I add my initial to my change, I can find my equilibrium amounts of both of these ions, right? So magnesium has a concentration equal to S. Fluorine has a concentration equal to 0.042 plus 2S. Okay, and so now I'm going to set this equal to my KSP expression. So my KSP, which is 7.4 times 10 to the negative 9th, is equal to my concentration of magnesium times my concentration of fluorine squared. Okay, so just like in the last problem, I'm going to plug in my equilibrium values, and I'm going to again ignore this 2S portion for fluorine. Okay, and so from here, I can solve for S, which is 4.2 times 10 to the negative 6th molar. That is the concentration of magnesium needed to be at our KSP. Okay, and so if our concentration of magnesium is higher than this number at all, right? If the concentration is higher than this, then precipitate will be forming, right? And this is a topic that we'll talk about in a few minutes. Okay, are there any questions on these problems before we move on into tonight's real content? Okay, and this is kind of just talking about what we will look at, right? So we'll start off looking at the common ion effect and how that plays a role in this chapter. We'll look at precipitation, right? So that fourth problem kind of touched on it, but we'll kind of describe how we know if a precipitate will form or if more solid can continue to dissolve. Then we'll kind of touch upon, I think, the really big topics in this chapter, right? I think common ion effect is a pretty good and important topic, but selective precipitation and ways to drive a reaction forward are both really good potential questions for your exam on Friday. Okay, and so if there are no questions, if people don't mind just typing their net IDs into the chat to sign in, and also just to indicate that you're ready to go over the new material. Okay, and while people are signing in, I'll just kind of keep this slide up for a moment, just so you guys can kind of read it and digest it, write it down, whatever, before I start explaining it. Okay, I think everyone's signed in, so I don't think there are any questions remaining. And so we talked about the common ion effect a little bit in chapter 15, but it really plays a pretty big role in this chapter. Okay, so we're going to see the common ion effect anytime an ion is present in a solution from multiple chemical species. Okay, and so in this chapter, right, think about question number 3, where it was iodine or iodide that was present from 2 sources, right? Typically, an ion is added as a salt, right? And so we're going to assume that that salt completely dissociates. And so typically, that salt and its concentration in solution is our initial concentration of that common ion. Okay, and the other place that we will see this ion get added to the solution is in terms of the solid that can partially dissociate. Right, okay, so again, common ion, it'll be added through 2 sources, typically a salt, and as that solid that will have equilibrium, that KSP. Okay, and a really important note, and this is probably a question that I fully anticipate you guys seeing on your final when you get asked about chapter 16 in terms of multiple choice questions. Okay, but the presence of the ion in the solution will decrease the solubility of the solid that contains that ion. Okay, and we'll prove this on the next slide, right? But an example of this is if you are trying to dissolve barium fluoride, right, you would actually find that barium fluoride is more soluble in pure water than it would be in 0.1 molar sodium fluoride, right? So here, fluorine is our common ion. And so because sodium fluoride contains an initial amount of that common ion, that fluorine, right, it will actually cause our solid, barium fluoride, to have a decreased solubility. Okay, and so again, let's look through an actual example that mathematically proves this. Okay, so we're going to investigate the solubility of lead bromide in two different 250 milliliter solutions, pure water and calcium bromide. Okay, and so we're going to, in both these solutions, they have the same volume, and we're to both of them going to be adding 30 grams of our solid. Okay, and the KSP in both solutions is going to be constant. It's going to be that 6.6 times 10 to the negative 6. Okay, so what I'm going to first do is convert from 30 grams of my solid to kind of like a concentration. Oh, I did that, but there's actually no real reason to do that, right? The reason why you actually don't need to do this, and I meant to kind of just ignore it, is that would be the concentration if your solid could completely dissolve, right? But our solid won't. Okay, and so in essence, that's not really necessary to do. Okay, and so my first calculations here at the top are for in my pure water solution. Okay, and so again, this is kind of my initial amount of lead bromide, but again, the amount of initial solid we have is just irrelevant to the problem, and we just don't care much about it. Okay, so I'm going to write my equation. So lead bromide solid is going to ionize into lead 2 plus and 2 molecules of bromide or bromine. Okay, now because we're in pure water, we're not going to have any initial amount of either of our ions, right? And so we're just going to have a change that we're going to put in terms of S. So for lead plus S, for bromine plus 2S. And so we'll write our equilibrium concentrations in terms of S. Okay, and now we're going to relate this to our KSP. So our KSP, which is 6.6 times 10 to the negative 6, is going to be equal to our equilibrium concentration of lead 2 plus, which is equal to S, times our equilibrium concentration of bromine minus, which is 2S. And because its coefficient is 2, we're going to square it, right? So 2S squared. And so when we go through our algebraic manipulation, right, this is really equal to 4S cubed. And again, that's equal to that 6.6 times 10 to the negative 6 value. Okay, and so when we solve for just the value of S, it comes out to 0.0118 molar. Okay, and so again, that's kind of relatively showing us how soluble lead bromide is, right? It's able to create those concentrations of ions. Now let's look at the solubility in calcium bromide, okay? So we're told that this solution is 0.35 molar in terms of calcium bromide, okay? But we only really care about bromine. We don't care about the calcium portion. So we're gonna convert this to molarity of our bromine ion, which is really equal to 0.7 molar bromine. Okay, and so because the solution already has that concentration of bromine present, we're going to plug that in for our initial amount of bromine in our ice table. Okay, and so again, see how that's the difference, that when we have a solution that has a common ion, we are going to have an initial concentration of that common ion, right? We didn't have an initial concentration of bromine in water. We do in this calcium bromide solution. Okay, so again, I'm going to write my ice table. My initial amount of bromine is 0.7 molar. My change for lead is still plus S. For bromine is plus 2S, just like before. And so now our equilibrium amounts of our ions are S for lead and 0.7 plus 2S for bromine. Okay, and we're going to set these equal to our KSP. Right, so our KSP, which is 6.6 times 10 to the negative 6, is equal to our equilibrium concentration of lead, 2S times our equilibrium concentration of bromine, which is 0.7 plus 2S. And again, we have to square that because our coefficient of bromine is 2. Okay, now we're going to ignore this 2S portion because in almost every problem, it's super small and doesn't actually affect the number that it's getting added to, right? So we simplify that expression to S times 0.7 squared. And when we solve for S here, it comes out to 1.35 times 10 to the negative 5th molar. Okay, so comparing the two S's we solve for, right, we can see that the number is much bigger, right? The solubility is much bigger in the pure water sample than it is in the calcium bromide sample, right? Again, our concentration, it's a difference in magnitude of almost 1,000. Okay, so pretty substantially different. Are there any questions on the common ion effect? Okay, if there are no questions, then we'll move on to some terminology for solutions. Oh, I think maybe a question did arise. So it's not, to be more soluble visually is kind of tough, right? Because if something's soluble, right, think of when salt dissolves in water, right? If something's soluble, you don't actually see it, right? Because it goes into tiny ions. But if something is more soluble, right, kind of imagine, again, kind of in like salt water, if something's more soluble, it just means that you can add more solid and it will disappear. Okay, and so basically, if we go back, right, we can see that lead bromide is more soluble in water than the calcium bromide solution. So if we added, let's say, I don't know, if we added the same amount of solid to both of these solutions, right, the water solution and the calcium bromide solution, there would be more undissolved solid at the bottom of our calcium bromide solution than there would be in water. Does that make sense? Okay, yeah. Yeah, again, it's kind of hard because solubility, again, it's kind of almost a lack thereof seeing solid at the bottom. And so if something's more soluble, you can basically just add more until it starts to kind of just accumulate at the bottom. Okay, I think this terminology and the precipitation relationships we talk about here might help make that make a little more sense. Okay, so let's talk about precipitation. Okay, and so in this chapter, when we talk about precipitation, we're really going to be relating Q to our KSP, right? We're relating Q and K. Okay, and so remember that Q and K overall, they're calculated exactly the same, and generally they are products divided by reactants. Okay, and so if our Q is less than our K, or our KSP in this case, that means we haven't formed enough product and we have too many reactants compared to equilibrium, which is our KSP. And so whenever Q is less than K, or our KSP, our forward reaction will be favored, right? And so below, I put a little example reaction of the dissolution or kind of ionization of copper hydroxide, right? So our reactant is a solid and our products are the ions it can split into. So if Q is less than K and our forward reaction is favored, that means that we're going to be dissolving more ions, right? If we keep adding a little bit and a little bit more copper hydroxide, it'll disappear, like we won't be able to see it because it's going to turn into its ions. Okay, and it means that, again, you can keep adding more until you reach your KSP, right? When your Q is equal to your KSP, that means that you are at equilibrium, and that means you're at your saturation point. Okay, and we'll talk about saturation point in just one moment. Okay, and if your Q is greater than your KSP, right, that means you almost have too many products, not enough reactants, compared to equilibrium. And so your reverse reaction will be favored, right? Well, our reverse reaction is when we take products and convert it to reactants. Okay, and so when we're looking at that for the dissolution or solubility of a solid, right, if our reverse reaction is favored, we'll actually form a precipitate, right? We'll form a solid, okay? And so it's very, very significant when your Q is greater than your KSP, again, because you'll be forming solid. Okay, and that was kind of the premise behind that challenge problem number 4 that we just went through. Okay, now it's really hard to talk about precipitation and solutions in general if we're not familiar with our solution terminology, right? So just to kind of review terminology that somewhat we covered last semester, but some of it's somewhat new, right? So unsaturated means that you have not reached your saturation point yet, right? Unsaturated solution corresponds with Q being less than your KSP. It means that you can dissolve more of that solid into its respective ions. Okay, so unsaturated is basically when our Q is less than our KSP. A saturated solution means that you have dissolved as much solid into ions as you can, right? That corresponds with Q being equal to your KSP. Okay, now something to note about a saturated solution, not only are you at your KSP, but sometimes people think of a saturated solution as, you know, you're making salt water and you add a bunch of salt and you notice some accumulates at the bottom, right? That means that you have added too much salt, no more can be dissolved. That is not saturated, okay? If you have a saturated solution, you actually will not see any accumulation of product, right? It means that every single molecule that you added would have split into its ions. Okay, that's saturated solution. If you have a solution and you see an accumulation of solid at the bottom, that means that you have a supersaturated solution. Okay, and that means that you added more solid than can physically be dissolved. Okay, that's why there is an accumulation. Okay, and it corresponds with Q being greater than your KSP. Okay, basically you added too much product. You're going to be actually supersaturated doesn't really correspond with Q being greater than your KSP, right? Because supersaturated typically means that you added too much solvent, or you added too much solute and no more can be dissolved. Q being greater than KSP, typically that situation is when you have ions, right? So you add ions to solution and their concentrations get too great so that your Q is greater than your KSP, which causes solid to form on the bottom. Okay, so it's kind of an ordering, right? Q being greater than KSP is you added ions and you have too many, so a solid appears when you never added a solid originally, or you didn't add that particular solid originally. A supersaturated solution, typically you add that solid that's only partially soluble and no more can dissolve after that point, after the saturation point. Okay, please let me know if that was confusing, because I'm happy to re-explain that. And then lastly, a terminology that you see in lecture a few times, so I wanted to point it out, was whenever you see dissolution, it kind of just means dissolve, or more can be dissolved. Okay, so when kind of the term dissolution, we correspond to, it's an unsaturated solution, or our Q is less than our KSP. Okay, is everybody okay with this? And okay with me to move on to, I believe we have an example on the next slide. Okay. And so again, we are going to look at an example. Okay, so this is one, right? We're going to add barium chloride and ammonium fluoride, right? And we are going to see does a precipitate or a solid form, right? And so we're told that the KSP of barium fluoride is 1 times 10 to the negative 6th, right? So realize here that this is just like a chapter 4 problem. We added barium chloride, where one of the ions, the barium portion, will go on to potentially form a solid. And from our other salt, ammonium fluoride, that fluoride portion is going to try to combine with the barium from the other salt to produce a solid. Okay, and so again, will a precipitate form? So what I'm going to do is I'm going to take each individual salt, right? I'm going to take the mass of it given. I'm going to convert from milligrams to grams. And for both of them, I'm going to use the molar mass of the respective salts to convert from grams to moles. Now that I have moles of each of these individual salts, I'm going to convert to moles of the ion I care about, right? I don't care how many moles of barium chloride or ammonium fluoride I have. I only care how many moles of fluorine and barium I have. Okay, so once I have moles of those individual ions, I'm going to divide it by the volume of the solution, 275 milliliters or 0.275 liters, and that'll give me the concentration of each of these ions. Right, so the concentration of barium will be 2.15 times 10 to the negative 4th molar, and my concentration of ammonium fluoride is going to be 0.019 molar. Now that I have these concentrations, I'm going to write my KSP equation, right? So my KSP for barium fluoride, right, and it's really important to note that there's 2 fluorines per 1 barium atom, right? My KSP of this will be equal to my concentration of barium 2 plus times my concentration of fluorine minus squared, right? Because if you wrote out the ICE table, the coefficient for fluorine would be 2. Okay, now these concentrations that I solved for, right, I don't know if I'm at my KSP or if I'm past it, before it, I'm not sure. So I'm going to plug it into Q technically, okay? But remember that we calculate Q exactly how we'd calculate KSP. Okay, so to solve for Q, I plug in my concentration of barium and my concentration of fluorine, remembering to square it, and I find that Q is 7.76 times 10 to the negative 8th molar, or actually, I don't think there are units, so I apologize, it's not molar. Okay, and my KSP, which was given, is 1 times 10 to the negative 6th. Okay, so in this case, our Q is less than our KSP, which means no precipitate will form, right? In order for precipitate to form, we'd have to add more barium chloride or more ammonium fluoride in to some degree so that our Q is greater than our KSP, right? Precipitate will only form when our Q is greater than that KSP value, okay? And again, we could do that by adding barium chloride and only that. We could do that by adding ammonium fluoride and only that, or we could do that by adding a combination of both. Okay. Any questions on this before moving on? Okay, so a pretty big topic in this chapter, especially in terms of solving problems, is selective precipitation. Right, so if we have 2 cations in solution, right, so 2 ions with positive charges, we can separate these ions from each other by adding an anion that will precipitate with only one of these cations, right? That's one way to physically separate those cations. Now in this chapter, we kind of see a derivative of that, right? Typically, we don't add an ion that only forms a precipitate with one cation, right? Typically, we add one that can form a solid or a precipitate with both, okay? But each solid will have a different KSP, okay? And so this allows us to partially separate one ion from another. Okay, and I think the best way to understand selective precipitation is just to look at a problem. Okay, and so on the next slide, we'll go through a problem, but your typical problem asks for two things, right? The first thing that they will ask is which solid precipitates first. Okay, that'll pretty much always be one question that you receive. Okay, which one precipitates first? The second question will typically ask what percentage of the ion that does precipitate first, what percentage of that has precipitated when the other ion starts to precipitate, right? And so I believe Dr. P went or taught these lectures. I think he did a really, really good job laying out this whole chapter very, very clearly and kind of just dedicating one lecture video to one topic. And so he goes through, I believe, two really good examples of selective precipitation. Okay, and this problem is going to be very similar to what how you saw him go about these problems. Right, so we have a solution that's 0.18 molar silver and 0.052 molar barium. Right, so again, we have two cations in solution. As you start to add potassium chromate, right, and so before I continue on with this problem, realize that silver and barium are both cations. So when we add a salt like potassium chromate, if you already have cations in solution, the cation portion of this salt doesn't matter, right? So the potassium part we couldn't care less about. What we care about from this salt is the chromate portion. Okay, so as we start to add this potassium chromate, we notice precipitate starts to form, right? And you would actually see at the bottom of a test tube some solid starting to just randomly appear out of seemingly nowhere, okay? And so you're asked, what is the identity of that precipitate? And then also, what percentage of the cation that precipitates first will have precipitated when the second one starts to form? Okay, and so we're given not only the equation, but also the KSP of silver chromate and barium chromate. Okay, so in this portion, right, I'm just going to solve for what concentration of that chromate ion that can combine with either cation, right? What concentration of chromate I need in order to reach my KSP, right? Because as soon as you go over that concentration we solve for, precipitate will start to form. Okay, so I'm going to start with silver chromate. Okay, and so my KSP for this is equal to 1 times 10 to the negative 12th. Now, if you wrote out your equation for this, right, you'd find that it dissolves into 2 atoms of silver and 1 molecule of chromate, right? And so our KSP expression should be equal to the equilibrium concentration of silver squared times our concentration of chromate. Now, if you were to write an ICE table, you would have that the concentration of silver at equilibrium is 0.18 plus 2s squared times the concentration of chromate at equilibrium, which would be equal to S. Okay, but again, in this chapter, we can kind of always ignore that plus 2s portion that we would have seen for silver, right? So I'm just gonna kind of simplify it and just plug in my concentration for silver and solve for my concentration of chromate. Okay, and so when I plug in my concentration of silver, I find that I would need my concentration of chromate to be 3.09 times 10 to the negative 11th molar in order for me to start forming precipitate. Okay, now I'm going to use the same exact process to solve for the concentration of chromate needed to, for barium chromate to start to precipitate or start to form. Okay, now the KSP for this is equal to 1.2 times 10 to the negative 10th, which is equal to my equilibrium concentration of barium times my equilibrium concentration of chromate. Now again, we're going to assume that the initial amount of barium I have is my equilibrium amount of barium, so 0.052. So what I find by going through this calculation is that in order for barium chromate to start precipitating out or starting to form solid, I would need a concentration of chromate equal to 2.31 times 10 to the negative 9th molar. Okay, and it's really important when you answer which solid precipitates first that you choose the one where this ion, this common ion that you solve for, in this case chromate, has the lower concentration needed to reach your KSP, right? So the silver chromate, we require a lower concentration for this solid to start to form, okay? And so silver chromate will precipitate first, right? And that's what this first sentence kind of says. Okay, that one will precipitate first. Now the second part of the question basically asks how much of my silver, which is that cation that will precipitate first, how much of my silver will have precipitated when my barium chromate starts to precipitate, right? Because barium chromate is the solid that will start precipitating second or later on. Okay, and so to solve for this, what you're going to do is you're going to take your KSP equation for the solid that will precipitate first, right? So silver chromate will precipitate first, and its KSP is equal to 1 times 10 to the negative 12th, and that's going to be equal to my silver concentration squared times my chromate concentration. Okay, and here we're going to solve for a concentration of silver. Okay, and so the value that we are going to use here for chromate is going to be the concentration of chromate required or needed for barium chromate to start precipitating or start forming, right? And so barium chromate starts to precipitate when chromate's concentration is 2.31 times 10 to the negative 9th. So I'm going to plug that value in, and then I'm going to undergo algebraic manipulation to find what would my concentration of silver be in the solution when, again, 2.31 times 10 to the negative 9th is my chromate concentration. And so what I find is that my concentration of silver would be equal to about 0.021 molar. Okay? And it's important to note that this represents the amount of silver still present in the solution. Okay, so it's not the amount that has precipitated out, it's how much is still remaining in the solution. Okay, and so my next step to find these percentages, I'm just going to solve for what percent of my silver is still remaining in solution, right? Which is going to be the concentration of silver I just solved for, 0.021, divided by my initial concentration of silver given in the problem, 0.18. Okay, I'm going to multiply it by 100 to turn it into a percentage, and I find that about 11 2/3% of my initial silver is still remaining in solution as ions. Okay, now that wasn't the question, however. It was how much or what percent of silver has precipitated. Well, if 11.67% is still in solution, right, then all the rest of the silver must have precipitated as solid. Okay, so the percent of precipitated silver will be 100% minus that 11.67%, which is equal to about 88%. Any questions on this? Before moving on to our last little topic for tonight. Okay, so the last two lecture videos given for this chapter were ways to drive a reaction forward or ways to dissolve more solid. Okay, and there were two main ways that were introduced, right? So the first method, I believe, was in video 7 from chapter 16. The second method was covered in the last video, video 8 of chapter 16. Right, so we can dissolve more solid by adding strong acid, right? So remember, strong acids completely dissociate. So by adding strong acid, we're really just adding protons or H+. Okay, and so what will happen is when we add strong acid, it will react with the anion portion from our solid, right? And this will pull the reaction forward, okay? Now, it happens to a greater extent when liquids or gases are formed, right? But we'll most often see this when our solid contains hydroxide, right, OH minus, carbonate, CO3 2-, sulfide, S2-, or phosphate, PO4 3-. Okay, so if you ever see any of these portions as part of your solid and you are adding acid or you're in an acidic solution, should kind of have alarms going off saying, oh, my solubility will increase because adding that acid or having that acid will pull my reaction forward. Okay, now we can also see this by not just adding a strong acid, but instead we could form a complex, right? And so this is kind of like KF when we're making complex ions, which was introduced earlier this chapter, right? In one of the more likely scenarios you'll see this where we're forming a complex is when we add ammonia, right? And this will react, the ammonia will react with a metal cation to produce a complex ion, right? And they'd probably give you an equation showing you this, okay? So you typically don't really need to make that jump, okay? But again, the ability to form this complex ion will pull the reaction forward, allowing, again, more of that solid to dissolve. Okay, and so really the whole idea behind this is we're going to utilize Le Chatelier's principle here, okay? And just kind of a note to remember is that here we're going to have almost multiple equilibriums, right? That we're going to add these equilibriums together. And remember that when we do this, you're going to multiply the K values to find the new K value of that added equation. So let's look at a couple of examples. So let's look at the solubility of calcium hydroxide when we add acid. Okay, so our normal equation is calcium hydroxide solid goes into calcium and hydroxide, 2 hydroxide specifically. Now, if we add acid to this system, right, we add strong acid, H+, what's going to happen is this H+ is going to react with hydroxide to produce water, right? And this H++ hydroxide, it has its own equilibrium constant, right? It would be 1 over Kw. And our calcium hydroxide will have a KSP. Okay, but what basically happens is H+ reacts with the hydroxide, which is a product in this first equation, right, to produce water. Okay, so in essence, the presence of H+ is taking away OH-, right, because it's producing product. So the amount of OH- is essentially decreasing. Okay, so thinking about Le Chatelier's principle, if the amount of product that we have is decreasing, right, we are going to counteract that change by shifting to the right and forming more products, right? Basically, more of our solid is going to dissolve because we're decreasing our hydroxide concentration by reacting it with acid. Okay, and so if we add these two equations together, right, and cross out things that appear on both sides, which would be hydroxide, it should really be 2 of all of these, but we would get a net equation of calcium hydroxide plus H+ goes to calcium 2+ plus water. Okay. Now let's look at other examples, right? What happens if we don't form water, right? Right? What happens if we have like carbonate instead of hydroxide as part of our solid, right? So barium carbonate solid would split into barium and carbonate. If we add acid, right, that acid will react with that carbonate ion to produce carbonic acid that will actually end up splitting into liquid water and CO2 gas. Okay, but again, essentially here, by adding the acid, it's going to react with our anion to produce other molecules. Okay, so by adding that acid, essentially we are decreasing the concentration of carbonate. And again, based on Le Chatelier's principle, if we're removing a product, that carbonate ion, right, our equilibrium, our KSP equilibrium will shift to the right to basically form more of that carbonate. How much acid do you add? You will not be, I really don't believe you will be asked that. I'd have to think about that. I don't think I've ever seen a question where that's ever been asked. Let me think. And if I can think of an example where you might be asked that, I'll bring it to next SI. But essentially, typically what they'll do, I guess they could ask you how much acid. What is a more likely problem is question 5 in the challenge problem. So I'll actually address it when we get there, right? The example used in lecture was you're actually told acid was added, and based on the amount of acid added, there was a certain pH. Okay, and so based on the pH, you actually know how much H plus there is, and you factor that into your KSP equation. Okay, but again, I'll touch upon that a little bit more when we get to the challenge problems. Okay, and again, just an example of a complex. Right here we have, so this is actually the exact example Dr. P used. Silver chloride solid splits into its respective ions. If we add ammonia, right, that will react with silver to produce a complex ion, right? Now this second equation has its own Kf, and basically the addition of this ammonia causes us to use up some of this silver. Therefore, we're decreasing the concentration of silver, causing more solid to dissolve in order to reestablish equilibrium. Okay, so I'm just going to leave each slide up for about 10 seconds so you can get a picture if you'd like. But again, these are posted as well. So here's a selective precipitation problem. Okay, it's 2 parts based on the same prompt. This third multiple choice question is actually, I think I changed the numbers, but it was on by exam way back when, right? So it's unknown compounds that we're just going to denote with random variables. They have similar molar solubilities. And so knowing the KSP of one of these compounds, you can actually solve for the KSP of the other one. Okay, that's number 3. Again, this is something that has appeared on an exam before. And then our last 2 challenge problems, where they're actually more activities, right? So number 4, I want you to rank solubility of a solid in multiple solutions. But then I want you as an activity to numerically prove your answer, right? It's quite a bit of work, but really it's really trying to establish the concept of common ion effect. Okay, and lastly, number 5, we said that the addition of an acid will increase the solubility of a solid. And so kind of prove that using the solubility of nickel hydroxide in pure water and a solution that contains 0.4 millimolar hydrochloric acid. Okay, and there's a little note at the end to kind of give you a little hint. Okay, again, kind of addressing the question, could they ask you how much acid you need to add? Potentially, they could. I think it's a really out there question. However, I'll try to think of one and make one for Wednesday. But I wouldn't have that as a forefront of your worry. I think what I've kind of provided in SI as examples, along with what Dr. P went over in all those lecture videos, is much more likely what you'll see. Also remember that Chapter 16, until your final, only appears on this exam coming up on Friday, which is long answer between chapters 15 and 16. And so my best guess is that your exam on Friday is either 3 or 4 questions. It's going to be a titration question, probably 1 buffer question, and likely just 1 chapter 16 long answer question. However, there could be 2. Okay, but I don't think you'll see too many curveballs, but I will try to think of a how much acid do you add question. But again, likely that's much harder than they'll expect you to be able to do. Okay, so I'm going to stop sharing my screen, but if there are any questions, as always, I'm happy to stick around and answer them.